Hello guys, this is Mike Tutors, and here we'll be proceeding on our topic theory of structures, talking about cantilever with a point load at its free end using double integration method for finding the angle of slope and the maximum deflection. Here is the diagram showing what we are to do today. So a cantilever is fixed at one end and is free at the other end, but here we'll be dealing on having the point load at the free end. So note, cantilever beams will have its maximum deflection at the free end, while for simply supported that we did in our previous lectures, we'll be having its maximum deflection at the midspan or the midpoint. So let's proceed into today's class. So here's the diagram, study it. Then here's the application, and now we derive the formula for slope and deflection. So this is mx representing maximum deflection at point x, and this is mx is w times minus w times x minus w times x. So the negative sign there is showing that is due to hugging. So mx, we have derived this in our previous class, that then bending moment, which is mx, is equals to ei the square y over the x square. So ei the square y over the x square, when we equate it, mx is minus w times x. So when we equate the two, we resolve it as equation 1. Then we proceed. So after we get the equation 1, don't forget we are dealing with double integration. So we integrate it firstly. We integrate equation 1 firstly. So this is the integration sign. That will be ei integral the square y over dx square equals integral minus wx dx. For those that are familiar with integration in their mathematics, you put the x. So ei, when you integrate it, it becomes ei dy over dx equals minus wx square over 2 plus constant of integration c1, we represent as c1, or this for the boundary condition, so we call it equation 2. So don't forget, the formula for integration is x raised to power n plus 1 over n plus 1. So the power of x, 2 plus the power of x here is 1, so 1 plus 1, 2 over n plus 1, 1 plus 1, 2. So that's how we got this. So I'm going to be applying it to all. So when x equals L, which is the distance, dy dx equals 0. What we are just trying to do here is we are trying to get the boundary condition or the constant of integration c. Then we substitute it back into equation 2. So to derive that, we make x equals L and dy dx equals 0. So dy dx is 0, so this is 0. So when placed, you see x, you put L. So we resolve it to this minus wx square over 2 plus c1. So we plug c1 as wl square over 2. So we substitute it into equation 2. So we got this ei dy over dx equals minus wx square over 2 plus wl square over 2. Sorry, I'm a bit fast, but to get this thing right, make sure you put something down. So the faintest ink is better than the sharpest brain. So learn to put something down, put things down. So we resolve this to equation 3. So the next is When we get this equation 3, the first thing we are going to get after doing the first integration, we get the slope, the maximum slope. So to get the maximum slope, we say x, we substitute x equals 0. Any place you see x, you input 0. So we will get ei dy over dx equals, this will become 0. So to remain this ws square over 2. So we just here we represent the y over dx, we interchange it with I at point B, or you can put theta, meaning the angle of the slope. So when you do your subject of the formula and make this stand on its own, it will become theta or I, anyone you use, because wl square then ei 2ei. So this is the formula for slope for cantilever with a point load at its free end using double integration. Then we proceed to second integration method. For the second integration method, we integrate equation 3 that we derived previously. So I skip some steps here, so just put something down and follow me. So this is equation 3 ei this, then you integrate it, you put in the sign, integral sign. So we will resolve it to this ei divided by this equals, here I already integrated this. So we bring out the coefficients, that's minus 1 over 2, then wx, x is having power of 2, so 2 plus 1 over 2 plus 1, which is power of 3 over 3. Then do the same here. So we get the second constant of integration, call it C2, or the boundary condition. So ei, when we integrate this, when we integrate the y over dx, we get y at that point, by using point B at point B equals this, to 2 times 3 6 ws over 3 plus this. So in this place, what I did here was that we are having x raised to power 0, sn raised to power 0 is 1. So that's what was here. X, an invisible x is here. So just imagine x raised to power 0 here. So 0 plus 1 over 1. So this is wl square x over 1 plus c2. So we proceed to resolve it as this and get equation 4. Then when x equals L, y equals 0, so we substitute x at a particular distance equals L and y equals 0. So in this place we are trying to get C2, which is the constant of integration. So when we substitute the value, we will resolve it to this. Then we get the value of C2. This is just simplify this place for better understanding, so you can digest it well. So we find the lowest common multiplier, then we get this C2 at the minus wl cubed over 3. So we substitute C2 into equation 4 as we did for the first boundary condition. We substitute it into the previous equation, so we resolve it as this. So here I told you that when we want to do the second integration, we are trying to derive the maximum deflection. So when we do the first integration, we are trying to derive the maximum slope. So maximum deflection occurs at the free end, I told you previously. Then we substitute x equals 0 into the equation to get the maximum deflection yb. So we got it as yb equals minus wl cubed over 3ei, or simply you can put it as wl cubed over 3ei. So the negative sign here is just showing that it's deflecting downward. So in our next class we'll be talking about cantilever with a point note, not at the free end. Thank you guys. God bless you. Do like and subscribe to our channel, Wicked Tutors, and comment on our videos. Thank you very much.